Okay, hello everyone in a new video. So we have reached part 3 of chapter 8, which is the chapter of Newton's second law for rotation. Now, before we start, let me make the following remark regarding the previous exercise. So notice that in this case, in this exercise, if we recall in the previous part, we were determining the magnitude of the force F, in this case, knowing that the system is at equilibrium. So, and here, we have used the fact that summation of moments around the axis delta is equal to 0. And we didn't use anything related to the fact that sum of forces is equal to 0 vector, although I have justified that this is in a translational equilibrium. The thing is that, let me explain why we have used sum of moments is equal to 0 and not sum of forces. So let's consider the following note. So if you consider this beam, which is massless, being represented by this shape, and suppose for some reason here we have a force F1 like this, here we have a force F2, here we have another force F3, and here so as denoted like this, okay? So let's say this is the force F1 and this is the force F2 and this is the unknown force F3 that we wish to determine. So, and we say that this is the horizontal, so let me give some angles. This is theta, this is alpha, and this is beta. So in this case, like the previous exercise, in order to determine the value of the unknown force, say for example, which is F, so in order to determine the value of F, knowing that this is at equilibrium, so in this case we have two equations. We have sum of forces is equal to 0 and sum of moments around the axis delta is equal to 0. Both equations are true. So this is translational equilibrium, and this is a rotational equilibrium. Okay, but now the thing is that we can use either equations to determine the magnitude of the force F, but the thing is that if we need to use this equation, we need, so this is the sum of forces is equal to 0. So here on the left we need to place all the forces that are acting on the beam, and they are given by F plus F1 vector plus F2 vector is equal to 0 vector, and we know how to deal with this equation. We will project it along the x-axis and we will project it along the y-axis. So projecting it along the x-axis will give us the x component, projecting it along the y-axis will give us the y component, then we can determine the magnitude. So far so good, but notice that this equation is not correct. Okay, so this equation is not correct, and the fact that this is not the complete equation, because here at this point, suppose that this is the point A, then this is the point of contact between the axis of rotation. This is not axis of rotation. Usually we call this point to be the hinge. Okay, so here at the hinge there is because there is a point of contact between the hinge and the rod, so for sure there must be a force which is a contact force between the hinge and the rod and they didn't mention anything about it. Okay, so here there is a missing force that we don't know. For this reason we cannot use this equation. So suppose that this force is given by R, and typically we don't know anything about this force except for it is a contact force. Suppose it may be something like this, or probably like this. We don't know. It is the reaction force. We don't know in this case whether the reaction is downward, upward. Okay, so let me say also the following. In the case of when we have a support and we have the weight which is acting vertically downward, in this case the reaction will be vertically upward because it's simply opposing the effect of the weight. But in this case we don't know anything about R, so R must complete this equation. Okay, so because we have an additional force that we didn't take into account, we cannot use this equation in order to determine the value of F. Okay, so there is another force R that we didn't mention in the problem due to the point of contact between the hinge and the rod. Okay, so what about why doesn't R in this case, why didn't R appear in this equation? So true, in this case we need the sum of moments are given by the moment of R over delta plus the moment of F over delta plus the moment of F1 over delta plus the moment F2 over delta. So this is the correct equation for the moment, and it doesn't mean that what we have done previously is wrong. Let me explain why. In this particular case, moment of the reaction R is 0, because notice that in this case the line of action of R passes through the axis of rotation, and whenever the line of action of the force passes through the axis of rotation, this force doesn't produce any moment. So let me make the following important note. If the line of action of a given force is along, let me say, the radial direction, then this force does not produce any moment. And by the radial direction, it means that its line of action passes through the center of rotation or the axis of rotation. So let me repeat. If the line of action of a given force if the line of action of a given force F is along the radial direction, then this force doesn't produce any moment. Okay, so by the radial direction, it means its line of action passes through the axis of rotation. So notice that in this case, because the line of action of R passes through the axis of rotation, so notice that this is the line of action of R, and it's passing through the axis of rotation, so it doesn't produce any moment. Okay, for this reason, when we have used this equation, this term will not appear. Similarly here, we have used this fact previously. So what about calculating the moment of the force F2? So what we have done here is basically, this is the radial direction. Okay, and we then considered the tangential direction like this. And we have said that the moment of the force F2 around delta is equal to F2 tangential multiplied by the distance t. Why so? Because notice that now F2 can be decomposed into two forces. So F2 tangential, and this is F2 radial. So let me say F2R, and this is F2 tangential. Now notice that in this case, the radial component of the force F2, its line of action, it's passing through the moment, it's passing through, through the axis of rotation. For this reason, always, the radial direction doesn't produce any moment. And the moment is only due to the tangential direction. Okay, so previously we have used this fact. Now let's also, in order to make this idea concrete, let me also justify why we have taken the tangential direction here and the tangential direction here. Then we will explain again why the moment you do this reaction is 0, but if you need to consider the sum of forces, so R will be present here. So this is the radial direction like this, and let me consider the tangential direction. And we are considering the moment of the force F around the axis of rotation delta. Notice that we are considering this distance is very small, so there is no distance here. Okay, so all of these lines coincide with the point of rotation, which is this one. So this is the axis of rotation, which is here. This is the center. Now the force F, this force F can be decomposed into two parts. This is the tangential direction and this is the radial direction. So now if we project F along the tangential direction, this is F tangential, and if you project F on the radial direction, this is F radial. Okay, so we can use capital R or small r, it's the same. Now if you want to be very clear, the moment of the force F around the axis delta is due to two forces. Is due to the moment of the force F tangential over delta plus, or let me say like this, it is, okay, it is equal to the moment of the force F tangential, which is Ft, or let me say like this, Ft, we can put here vector, it's okay, over delta plus Fr over delta. Okay, but notice that if we also here we place the vectors, it's okay. Here we can place vector or remove vectors because we are not equating them with other quantities. Now in this case, always we don't calculate this part because this radial direction passes through the axis of rotation, which produces no moment. So in order not always to explain why this is 0, so no need always to explain this is 0, we always take it for granted that the moment of any force is only due to the tangential component of the force itself. Okay, so let me repeat this also for the force F1. So this is the radial, this is the tangential direction, F1 tangential. Here we can place vector, for example, and this is the radial direction, F1 radial. So notice that this component corresponding to the radial component of F1, because it's along the radial direction, produce no moment. So the moment of this force is given by 0. So we'll only consider the moment of this component of the force F1, which is the moment of F1 over delta, which is equal to F1 tangential multiplied by the distance t. Okay, so now if we refer back to this example, what is the moment of this force? There is no moment produced by this force because it simply passes. It's simply along the radial direction. What is the radial direction here? It is the line of action passing through the axis of rotations. So, and here let me also clarify the following, that this is not only the radial direction. Here there are an infinite number of radial direction. This is a radial direction. This is another radial direction. This is another radial direction. This is another radial direction. So the radial direction is any line of action, imaginary line passing through the center. So any force lying along these lines produce no moment. Okay, and in particular the reaction R. Okay, so now let's move on to this exercise. They are telling me exercise number 3. So let me make it clear, let me highlight it. So if the line of action of a given force is along the radial direction, then this force doesn't produce any moment or produce no moment. Okay, so this is extremely important. We will refer to it several times during the exercises. Now exercise number 3, they are telling me Layan, a student of grade 11, investigated the laws of static equilibrium for a set of forces acting on 1 meter ruler. So here whenever they are talking about static equilibrium, we can always think of sum of forces is equal to 0, and eventually we can think about sum of moments around any axis delta is equal to 0, around the axis delta. Now the mass of the ruler was 0.15 kilograms, so whenever the mass is involved, this means that the weight will be included. Its center of gravity was at its midpoint. So notice that if this is 0, this is 100, so the center of gravity will be at 50 exactly. Layan applied the forces shown in the adjacent figure until the ruler is in equilibrium. And here we are talking about two equilibriums. The sum of forces is equal to 0 vector, and the sum of moments is equal to 0. Number 1, give the name of the instrument that Layan used to measure the magnitude of the forces. We know that the magnitude of the forces can be measured using spring balance or dynamometer. Now in number 2, they are telling me draw a free body diagram to show all the forces acting on the ruler. This is the ruler. So we have the force F3 acting somewhere here. We have the force F1 acting somewhere here. We have the force F4 acting somewhere here. And we have the force F2 acting somewhere here. And the magnitude of the forces, this is okay, they are listed here, but there is one also force that we didn't represent, which is the weight acting at the center, which is here. So because it has a mass, it will be directly subjected to the weight. In the previous examples we didn't mention the weight because I have stressed on the fact that these beams or rods that we were considering are of negligible mass. Now in number 3, they are telling me show that the ruler is in translational equilibrium, so we need to verify that sum of forces is equal to 0 vector. So we need to verify, so how to deal with this equation? We need to verify, so this will give us two equations. We need to verify that sum of forces of x is equal to 0, and we need to verify that sum of forces of y is equal to 0. So here no need to consider this because, no need to consider this because the forces are completely parallel to the y-axis, so we only need to consider sum of forces of y is equal to 0. Consider the vertically upward is the positive direction. So let's calculate f1y plus f2y plus f3y plus wy plus f4y. And here we are talking about the components, and the components may be positive or negative. f1y, it's pointing in the positive direction, so it's plus 9, plus f2y pointing in the positive direction, it's 12.5, plus f3y, it's pointing in the negative direction and its value is given by minus 5, plus wy, which is given by minus m multiplied by g, plus f4y, which is minus 15. So it's equal to 9. So this term here is given by minus 0.15 multiplied by 10. So 9 plus 12.5, 21.5, minus 5, minus 1.5, and minus 15. So these will give us minus 20, which with minus 1.5 plus 21.5 is equal to 0. So verified, then the ruler is in translational equilibrium. Okay, so this is it for number 3. Now in number 4 they are telling me calculate the moment of each force with respect to the 0 mark of the ruler, knowing that the chosen positive direction is clockwise. So let me erase everything. So we are interested in calculating the moment of each force with respect to the 0 mark of the ruler, knowing that the chosen positive direction is clockwise. Now let me also say the following. Now we are calculating the moment of each force with respect to the 0 mark. So we are calculating the moment with respect to this point, but here we are not considering that the ruler is able to rotate around. So it is able to rotate around this point, but here there is no axis of rotation, there is no hinge. Okay, so we will calculate the moment with respect to this point. You can imagine as if there is an axis of rotation here, but actually there is no. And now let me represent here the weight, which is vertically downward like this. This is the weight W, and now we need to calculate the moment of each force. Okay, I repeat, there is no force acting here because we didn't consider any axis of rotation. We are just saying with respect to the 0 mark. Okay, even if you consider that there is a hinge here or axis of rotation, so there will be a normal reaction somewhere like this, but notice that this the line of action of R is along the radial direction because its line of action is passing through the center, so simply it will produce no moment. Okay, but since we didn't consider it in the case where sum of forces is equal to 0, so R doesn't exist in nature. Okay, so I repeat, here we are just calculating the moment of each force with respect to the 0 mark, but here actually there is no axis of rotation, as if we are supposing that there is an axis of rotation. So now let's calculate the moment of the force F1 produced over delta, which is equal to F1 tangential multiplied by the distance d. Now in this case, d, which is this distance, is given by 20 centimeters, which is 0.2 meters. Now F1 tangential, let's take this direction to be the positive direction of rotation, which is counterclockwise or anticlockwise. So notice that in this case F1 will rotate in the positive direction, so it's plus. So if this is, let me specify the radial direction. So the radial direction are all of these directions. It is this one, this one, this one, this one. So in order to determine the tangential component of the forces, we will consider the radial direction passing through the center and cutting all the forces. Now in this case, notice that F1 completely lie along the radial direction. So it is simply F1 with no cosine. So the moment of the force F1 produced around the axis delta is given by F1 multiplied by d, and this is equal to 9 multiplied by 0.2, which is equal to 1.8 Newton meters. Now as for the moment of F2 around delta is equal to F2 tangential multiplied by d, in which d is equal to, so it is given by 90 centimeters, which is 0.9 meters. So now F2 tangential, notice that F2 will try to rotate the system in the positive direction, so it's a plus F2. Now as for the tangential direction, this is the radial direction, so the tangential direction is normal, so it's completely lying, so no cosine. So in this case, the moment of the force F2 on delta is equal to F2, so this being replaced here, multiplied by d, which is equal to 12.5 multiplied by 0.9. Plugging this on the calculator, 12.5 multiplied by 0.9, which is equal to 11.25 newtons meter. Now as for the moment of the force F3 around delta is equal to F3 tangential multiplied by the distance d, in which d is equal to, okay, suppose it's exactly 35. Here as it is indicated, it is 36, but let's use it 35 and we will check. So 0.35 meters. Now F3 tangential, for the same reasoning, now this it will rotate in the negative direction like this, minus F3. As for the tangential or the cosine, notice that it is completely tangent to the radial direction. So minus F3 multiplied by d, which is equal to minus 5 multiplied by 0.35, which is equal to minus 1.75 newtons meter. And I will keep this value here because I'm not sure whether it's 35 or 36 from the document. So we have 1.8 newton meter, 11.25 newton meter, and this one which is down. Let's proceed to the weight and F4. So the moment of the weight around the axis delta, so here we are supposing as if it is able to rotate around delta, but delta doesn't exist because we are telling with respect to the 0 mark. They didn't mention anything about axis of rotation. So it is equal to weight tangential multiplied by the distance d. D in this case is equal to 0.5 meters. And weight tangential, it is equal to, so notice that the weight is rotating in the positive direction, so minus, and the negative direction, which is mean clockwise. Okay, wait, and it is completely tangential, so no cosine. In this case, the moment of W over delta is equal to minus W multiplied by D, which is equal to minus the value of W is M multiplied by G multiplied by D, so minus 0.15 multiplied by 10 multiplied by D, which is 0.5. Plugging this on the calculator, then the moment of the weight produced around an imaginary axis delta passing through this point, although it doesn't exist. It's given by minus 0.5 in Newton meter. And now, as for the moment, we can erase this line. Of the moment due to the force F4 produced around delta, which is equal to F4 tangential multiplied by the distance D. D is equal to 0.7 meters. So F4 tangential is equal to, it will try to rotate the system in this way, which is in the clockwise, which is negative F4 multiplied by the value of the cosine. In this case, it's completely tangential. Then the moment of F force over delta is equal to minus F4 multiplied by D, which is equal to minus 15 multiplied by 0.7 on the calculator. (10.5) minus 10.5 in Newton meter. And here, let me calculate. Okay, so we are done with part 4. Now in part 5, so sorry, here they are telling me that the chosen positive direction is clockwise. Because already I have chosen it to be anti-clockwise, let me change the question and say it is anti-clockwise. Okay, so now let's calculate the sum of moments of part 5. So sum of moments is equal around an imaginary axis delta passing through the starting point of the ruler, which is this point. So the moment of F1 over delta plus the moment of F2 over delta plus the moment of F3 over delta plus the moment of the weight over delta plus the moment of F4 over delta. We are just calculating the sum of moments. Now the moment of F1 over delta is given by 1.8 plus F2 delta is given by 11.25 plus F3 delta, this is we are not sure about, is given by minus 1.75. So we will try to change it if we didn't achieve a reasonable number. And M weight delta is given by minus 0.75 plus F4 delta, which is given by minus 10.5. And let me check that this is consists of 5 terms due to 5 forces acting and not passing in the radial direction. Let me try on the calculator. So it's given minus 1.7. If we try to change 0.35 to 0.36 and multiply it by 5, this will give us 1.8. So minus 1.8 instead of minus 1.75 plus 1.8 plus 11.25 minus 12. Sorry, this is minus 10.5. Let me repeat the calculation again. $1.8. So 0.05. So yes, as expected, that here, notice that the weight is exactly lying on 336, so this must be changed to 36, and this is 36. This eventually will be 1.8, and now let's try this again. So this will cancel out with this. This with this will give us minus 11.25. With this, it will be 0. So in this case, sum of moments around delta is equal to 0. What is the conclusion? The conclusion is the ruler is under rotational equilibrium. Okay. So let's do just a small recap, or one should not forget the note that whenever the line of action of a force is along the radial direction, that it produces no moment. Okay. So that's it for me in this video, guys. In the next part, we'll complete solving this exercise and another exercises and explanation on this chapter.